noticed that the whiteboard was sort of invisible from the back last time. So fortunately, I have some slides that I prepared for this lecture. But whenever I give a lecture using slides, I tend to zip through them. And the last time I gave this lecture, I ended a bit early. So feel free to interrupt me and ask me questions during this lecture. We'll have plenty of time. OK, so why is the title different? I can't necessarily answer your questions, but I'll do my best. All right, so I would like to talk today about, give you a little bit of an introduction to the subject of chromatic homotopy theory, and specifically to tell you about certain cohomology theories called Morava K-theories. So, starting point, we're doing algebraic topology, and our goal in algebraic topology is to understand topological spaces by assigning algebraic invariants to them. So one of the most useful and interesting invariants that you can assign to a topological space is its cohomology. So the cohomology of a space X with coefficients in some abelian group A. So like a lot of important invariants in mathematics, there's a lot of different points of view from which you can approach this. There's a lot of different definitions that you can give for these cohomology groups. And this led Eilenberg and Steenrod to approach the subject axiomatically. That is, they wanted to characterize cohomology by saying that it was an invariant that satisfied certain axioms. So I'm going to give you more or less what the axioms that they wrote down said. So what is cohomology? Well, first of all, it's a functor. So it's something that assigns to every topological space X a sequence of abelian groups called the cohomology groups of X. And to every continuous map from a space X to a space Y, there's some map from the cohomology of Y to the cohomology of X that I'll denote by F upper star, if F is the name of the map. So this has a consequence. If you have a space X and you distinguish a base point, little x, that gives you a splitting of the cohomology of capital X into the cohomology of just the one-point space, its base point, plus some auxiliary factor. So that factor is usually referred to as the reduced cohomology of X. So cohomology is a homotopy invariant. One way to say that is that if F and G are two maps of between the same topological spaces that are homotopic to one another, then they induce the same map on cohomology. Cohomology is multiplicative, meaning if you want to compute the cohomology of a disjoint union of many spaces X alpha, that's just the product of the cohomology groups of the individual spaces X alpha. Now, these cohomology invariants, there's a cohomology group for every n, but these cohomology groups are related as n varies. And one way to describe the relationship is to say that they're suspension isomorphisms. If you want to know the nth cohomology group of X, and I mean reduced cohomology here, that's the same as the n plus first cohomology of the suspension of the space X. Cohomology has excision, or it has various long exact sequences. And one way of saying this is that if you have a space X, and inside that space you have a nice subspace Y, then any cohomology class on X, which vanishes when you restrict it to Y, has to come from the cohomology of X mod Y, meaning the space that you get by taking X and collapsing the subspace Y to a point. And finally, there's the so-called dimension axiom, which is a normalization condition. So this tells you what the cohomology of the one-point space looks like. So this should be the abelian group A in degree 0 and 0 in all other degrees. What's that? 4 is a structure, correct. So Eilenberg and Steenrod proved that if you have any invariants satisfying these axioms, then it was cohomology with coefficients in a certain abelian group A. And if you want to know what that abelian group A is, well, that's the abelian group that you can extract by taking the 0th cohomology group of a point. So subsequently, people realized that there were a lot of interesting examples of algebraic invariants that satisfied most of these conditions, but failed to satisfy the dimension axiom. So these were originally called generalized cohomology theories or extraordinary cohomology theories. Nowadays, they're just called cohomology theories. A cohomology theory is an invariant of topological spaces that satisfies the first 5 axioms that I listed, not necessarily the dimension axiom. And as mentioned earlier, really we should say a cohomology theory is not just these invariants individually, but also the data of these suspension isomorphisms. Those are part of the data rather than a condition. So one of the most important examples of a cohomology theory, other than ordinary cohomology, was introduced by Atiyah and Hirzebruch. It's called complex K-theory. So let's say that X is a nice finite space, like a finite cell complex or a compact manifold or something like that. Then you can look at the collection of complex vector bundles on X up to isomorphism. The set of isomorphism classes has an addition given by taking direct sums of complex vector bundles. And that makes this collection of isomorphisms into a commutative monoid. Now this commutative monoid is usually not an abelian group. You can add vector bundles together, but you can't subtract them. But whenever you have a commutative monoid, you can build an abelian group by just formally adjoining additive inverses to anything. And if you do that in this case, you get an invariant which is denoted by K0 of X and called the complex K-theory of X. So an example is if X consists of a single point, in that case a complex vector bundle on X just means a finite dimensional complex vector space. Up to isomorphism, finite dimensional vector spaces are just determined by a natural number, which is their dimension. So this commutative monoid would be the monoid of natural numbers. And if you take the natural numbers and add inverses, you get the group of integers. So, so far what I've defined for you is K0 of X in the special case where X is a nice finite space, like a compact manifold. But you can extend this definition and define Kn of X when n is an arbitrary integer and X is an arbitrary topological space. Well, I won't give you that extension, but I will mention that it's an example of a generalized cohomology theory. It satisfies the first 5 of the Eilenberg-Steenrod axiom, but it does not satisfy the dimension axiom. So what happens instead is that when you compute the K-theory of a point, well, I just told you what K0 of a point is. It looks like the group of integers. More generally, Kn of a point looks like the group of integers when n is even, and it looks like 0 when n is odd. So rather than being concentrated in degree 0, it's instead periodic with period 2. And that periodicity is the content of the Bott periodicity theorem. So let me go back and talk about cohomology theories in general for a moment. One of the most important things that you can say about cohomology theories in general is that they're always representable. So let's say I give you a cohomology theory. Remember, that means a sequence of invariants of topological spaces. Brown representability is the statement that in this situation, each of these ENs is actually a representable functor in the homotopy category of topological spaces. In other words, for each n, there's a space Zn such that the nth cohomology group of X can be identified with the set of homotopy classes of maps from X into the space Zn. But now remember that a cohomology theory is not just these individual invariants En. There's also a relationship between these ENs. There are these suspension isomorphisms that tell you how En is related to En plus 1. And this gives you a relationship between these spaces Zn and Zn plus 1. Specifically, it tells you that each Zn is homotopy equivalent to the loop space on Zn plus 1. So this motivates what's the foundational definition for the subject of stable homotopy theory. So a spectrum is a sequence of pointed topological spaces Zn together with a homotopy equivalence from each Zn to the loop space on Zn plus 1. So what's the point of this definition? Yes?
So why to choose the word spectrum for these family of spaces?
The reason that that's called spectrum in algebraic geometry, but I don't know the reason this is called spectrum in topology. But I think it is unrelated. So a spectrum is a sequence of pointed topological spaces, each homotopy equivalent to the loop space on the next. And the point of this definition is En, E, or I should say, where En of x is, as described before, the collection of continuous maps from x into Zn modulo the homotopy. You should remember the homotopy equivalence. Together with these homotopy equivalents. And you need the spaces to know what these individual invariants are, and you need the homotopy equivalences to write down the suspension isomorphisms. So every spectrum determines a cohomology theory, and the Brown representability theorem lets you go the other way. It tells you that every cohomology theory comes about in this way, and in fact you can be a little bit more precise. There's a bijective correspondence between cohomology theories up to isomorphism and spectra up to homotopy equivalence. So to a first order of approximation, this word spectrum is just a synonym for a cohomology theory. But for many purposes, this notion of spectrum is, you don't want to think of it as the same as the notion of cohomology theory. Thinking about the data that's described up here sort of reminds you that when you work with these objects, you're really doing a kind of topology. You're doing some kind of homotopy theory. So a spectrum, it's not the data of a topological space, but it's close. It's the data of a collection of topological spaces that are related to one another in some specific way. And when you work with spectra, you can do a lot of things that you do when you work with topological spaces. So there's a notion of spectrum, which is given by this definition. There's a notion of a map between spectra. There's a notion of a homotopy between maps of spectra. There's a notion of a homotopy equivalence of spectra, which I'm implicitly referencing here. And this sort of homotopy theory of spectra is the subject of stable homotopy theory, the object of study in stable homotopy theory. And that homotopy theory is to some extent forgotten when you think about these things just as cohomology theories. And for some of the things that I would like to talk about in tomorrow's lecture, it's important that you don't forget that homotopy theory. Okay, so let me give you some examples. Well, the motivating example of a cohomology theory is ordinary cohomology with coefficients in an abelian group A. So special case of the Brown representability theorem is that for any abelian group A, there's some space, which is usually denoted by KAN, such that the nth cohomology of any space X can be identified with homotopy classes of maps from X into this space KAN. So these spaces KAN are called Eilenberg-MacLane spaces, and there's lots of ways of describing them, but one of the simplest is they're characterized by saying what their homotopy groups look like. The homotopy groups of an Eilenberg-MacLane space KAN are concentrated in degree n, and in degree n you just see the abelian group A. And now if you look at these spaces KAN as n varies, they give you an example of a spectrum. Each KAN can be identified with the loop space on KAN plus 1. So this sequence of spaces is a spectrum which is typically denoted by HA. It's the Eilenberg-MacLane spectrum of A. And that's the spectrum which corresponds, in the dictionary of the previous slide, to ordinary cohomology with coefficients in A. So now I want to give you a series of analogies which are going to inform a little bit what I'm going to talk about today and what I'm going to talk about tomorrow. So I want to distinguish between, or I want to describe for you analogs in homotopy theory of certain familiar ideas in, I'll say classical algebra or non-homotopy theoretic mathematics. So first, in algebra, we can study situations where we have no algebraic structure at all. That is a situation where we're just talking about sets. And I want to think of the homotopy theoretic analog of just having a set as just having a topological space. And in classical algebra, one of the most important structures that we study is the theory of abelian groups. And I want to think of the analog of an abelian group in the setting of homotopy theory to be a spectrum or a cohomology theory. And let me remark that the right-hand side you can think of as not just giving you analogs of these classical concepts, but generalizations of these classical concepts. Any set can be regarded as a topological space by giving it the discrete topology. And any abelian group determines for you a spectrum by taking its Eilenberg-MacLane spectrum, by studying ordinary cohomology with coefficients in that abelian group. But the right-hand side is a generalization because there are topological spaces which are not discrete, and there are cohomology theories which are not ordinary cohomology. So in ordinary algebra, we study tensor products of abelian groups. That has an analog in the setting of homotopy theory. There's an operation on spectra called the smash product, which is sort of analogous to the tensor product. And once you have a tensor product, you can start talking about rings or algebras, as we did in the previous lecture. So in the sense of the previous lecture, if I took the category of abelian groups with its usual tensor product, the algebras are just associative rings. Similarly, in the setting of homotopy theory, you can study algebras in the world of spectra, which are called associative ring spectra. And you can study associative algebras. You can also study commutative algebras. There's a generalization of the notion of commutative ring, which is a commutative ring spectrum. So let me say a few words about these notions of ring spectra because they're going to come up today and they're going to come up again tomorrow. So what is an associative ring spectrum? Well, it's a spectrum E, which is equipped with some kind of multiplication, which is a map from E smash E into E, and it satisfies a suitable associative law. Now, one of the reasons that this subject is regarded as very technical is that there are a lot of different ways that you can make precise the idea that a multiplication like this should be associative. We're doing homotopy theory, so when we talk about associativity, are we asking for associativity up to homotopy, associativity on the nose? Well, there's a lot of different ways of answering these questions, and many of them give rise to the same or equivalent definitions. And rather than get into the details of any particular definition, let me instead just tell you how you can think about this notion of associative ring spectrum. So if you have any spectrum E at all, you can think of it as a cohomology theory. So it's an invariant that assigns to every topological space a graded abelian group. Now, if you have not just a spectrum, but a ring spectrum, then that invariant has more structure. To every topological space, you can assign not just an abelian group, but a graded ring. But to demand that this ring spectrum is associative, or A infinity, you demand more than just that you have a multiplication at the level of cohomology classes. Instead, associativity is supposed to somehow hold at the level of cocycles, at the level of objects that represent cohomology classes, not just at the level of the cohomology classes themselves. And we remark that it's a similar notion of commutativity, which will come up tomorrow, but not today. So let me give you some examples. Well, we've only met a couple of examples of spectra so far, but if R is an associative ring in the sense of classical algebra, then ordinary cohomology with coefficients in R is representable by this Eilenberg-MacLane spectrum HR, and that's an example of an associative ring spectrum. If R is a commutative ring, then you can regard HR as a commutative ring spectrum, and I've only given you one other example of a spectrum so far, or a cohomology theory so far, complex K theory. This is also represented by a commutative ring spectrum, which is typically denoted by K or by KU. in this statement that complex K-theory is represented by a commutative ring spectrum. So remember, complex K-theory has to do with vector bundles. If you want to class in the K-theory of X in degree 0, for example, you can represent that by writing down a complex vector bundle on X. And the way that you add classes in K-theory is by taking the direct sum of complex vector bundles. Similarly, which is by taking tensor products of complex vector bundles. Now that makes, for any space X, the K0 of X gets the structure of a commutative ring. Now that commutativity comes from the fact that if I give you two vector bundles V and W on the space X, then V tensor W is isomorphic to W tensor V. But that isn't just some weird coincidence that for every pair of vector spaces, V tensor W happens to be isomorphic to W tensor V. In fact, for every pair of vector bundles V and W, there's a canonical isomorphism between V tensor W and W tensor V. And if I wanted to, I could spend the entire rest of this lecture telling you all kinds of great properties that this canonical isomorphism has. I could show you slide after slide of diagrams that commute, where there are maps that say the tensor product is commutative, and maps that say the tensor product is associative, and maps that say there's some distributive law with respect to direct sums. I'm not going to show you any slides like that, but you can think of this statement that complex K-theory is represented by a commutative ring spectrum as having all of those commutative diagrams built into it. There's a multiplication not just at the level of K-theory groups, but at the level of things that represent K-theory classes, at the level of vector bundles. And the commutativity and associativity of the multiplication is something that you can, in some sense, see at the level of those representatives. Okay, so the easiest example of associative rings we talked about yesterday a little bit are fields. So let K be an associative ring. Recall that the following statements about K are equivalent. We can demand that every non-zero element of K is invertible. An equivalent demand is that every module over K is a free module. And if these conditions are satisfied, in the previous lecture I used the term division ring, a term which is sometimes used is that K is a skew field. And in this lecture I'll be a little bit sloppy and I'll just say that K is a field. So in this lecture, fields can also be non-commutative. So I would like to talk about some analogous notion in the setting of homotopy theory. So let's suppose that I give you an associative ring spectrum E. Well, the following conditions on E are equivalent. So you can take the E cohomology of a point, that's a graded ring, and you can demand that every non-zero homogeneous element in that graded ring is invertible. An equivalent demand is that any graded module over E star of a point is invertible. And the equivalence of A and B is not really a statement about topology at all. It's a statement about graded rings. For any graded ring, saying that all non-zero homogeneous elements are invertible is the same as saying that all the graded modules are free. But these statements have a consequence in the world of algebraic topology. If B is satisfied, well, you can talk about, you can think of E as an associative algebra in the world of spectra, and in the world of spectra you can study modules over E. And a consequence of these conditions is that every module over E in the world of spectra is a free module. So in this case, that means that it's something that looks like a direct sum of copies of E possibly that have been shifted. So if these conditions are satisfied, I'll say that E is a cohomological field. It's a cohomology theory that in some sense behaves like a field. So what are some examples? Well, let K be a field in ordinary algebra. Then you can build a cohomology theory out of that, cohomology with coefficients in K. It's representable by this ring spectrum, the Eilenberg-MacLane spectrum HK, and that's an example of a cohomological field. And this works if K is a commutative field, or more generally, if K is a skew field or a division ring. So the only other example that I've given you of a spectrum so far is complex K theory. The complex K theory is not an example of a cohomological field. Remember, K0 of a point is the ring of integers. And in the ring of integers, not every non-zero element is invertible. But the ring of integers is not a field, but you can extract fields from it by taking the integers mod p for any prime number p. And there's an analogous thing that you can do in the world of homotopy theory. So for any prime number p, you can form what's called complex K-theory mod p. So this is a cohomology theory, which in the language of stable homotopy theory, it's given by taking the cofiber of the multiplication by p map from complex K-theory to itself. And what does it look like? Well, the K mod p cohomology of a point looks like you take the K-theory of a point and you mod out by p. So the K-theory of a point, remember, was just a copy of z in every even degree. The mod p K-theory of a point looks like a copy of z mod p in every even degree. And as a graded ring, it has the structure that you might expect it to. It looks like z mod p adjoins some invertible element t, which lives in degree 2. So this graded ring has the feature that every homogeneous element, every non-zero homogeneous element is invertible. So K mod p is an example of a cohomological field. So now I want to ask the following question. So I told you that this world of cohomology theories with ring structures, you can think of it as a generalization of classical algebra. So classical algebraic structures live in this world, and there are also these more exotic structures like complex K-theory and complex K-theory mod p. And I want to ask if these more exotic structures are genuinely new examples, or are they somehow just some dressed up variants of ordinary algebraic invariants. So for example, how different is this cohomological field K mod p from the usual field Z mod p? So to answer this question, I would like to review for you a little bit of classical algebra. So recall that in ordinary algebra, if I give you a field, the most important question that you can ask about that field is what is the characteristic of that field? So you ask, is there a prime number p such that p is equal to 0 in the field K? If the answer to that question is yes, we say that K has characteristic p. Otherwise, we say that K has characteristic 0. But I want to give you a different way of thinking about the characteristic of a field. So let's say that K and K prime are two fields. They can be commutative fields or non-commutative fields. What does it mean for K and K prime to have the same characteristic? Well, an exercise for you from the usual definition of characteristic, or you could take this as a definition if you like. We say that K and K prime have the same characteristic if the tensor product of K and K prime is non-zero. So I'm giving you this funny definition of what it means to have the same characteristic because this definition will make perfect sense in the world of algebraic topology. So let's say now we have two cohomological fields, E and E prime. Well, there's an analog of the tensor product in the world of spectra, which is the smash product, and we'll say that E and E prime have the same characteristic if the smash product of E and E prime is not 0. Now, I haven't told you anything about this smash product. Let me just tell you one thing about it now. The smash product of E and E prime, whatever it is, it has the structure of a module over E. And if E is a cohomological field, one of the things I told you earlier is that any module over E is a free module. So this E smash E prime, it looks like a sum of copies of E possibly shifted. And if E prime is also a cohomological field, then this will look like a sum of copies of E prime possibly shifted. So if this smash product E smash E prime is not 0, it looks both like a sum of copies of E and a sum of copies of E prime. So an equivalent way of formulating this is that E and E prime have the same characteristic if you can find a copy of E inside a sum of copies of E prime, and you can find a copy of E prime inside a sum of copies of E. So using that description, it's not hard to check that this is an equivalence relation on cohomological fields. So with this definition here, I can make more precise the question that I wanted to formulate on the previous slide. I wanted to ask, complex K-theory mod P, it's a cohomological field, but is it really something new? Is it something new, or is it just a variant of Z mod P? So now we can ask this question, complex K-theory mod P, does it have the same characteristic as the ordinary field Z mod P? And as you might guess, the answer to this question is going to be no. The point is, that I'm trying to get across in this lecture is that in this more general world of cohomology theories with ring structures, we see some genuinely new phenomena. In this case, we see some genuinely new characteristics that fields can have. So,
in the past, the characteristics
what's that?
in the past,
In the past, characteristics, yeah, they're classified by either prime numbers or by 0. And I'm going to tell you about the classification of characteristics in this more general world now. Okay, so the first thing that I want to do is talk about how you could tell that two fields have different characteristics. So remember, these ring spectra, first and foremost, they're cohomology theories. And so what they give you is invariance of topological spaces. So I want to apply these cohomology theories to a particularly simple example of a topological space. So let G be the cyclic group Z mod P, and let X be the classifying space of G. It means the Eilenberg-MacLane space KG1. It's a space whose fundamental group is G, and it has no higher homotopy groups. So I want to tell you about the cohomology of this space X. So first, let's consider the cohomology of X with coefficients in a field whose characteristic is different from P. If K is a field of characteristic different from P, it turns out the cohomology of X looks just like the cohomology of a point. In other words, the invariant of cohomology with coefficients in K, it can't see the fact that X has this copy of Z mod P inside its fundamental group. From the point of view of this cohomology theory, X is no different from a point. Now you get a very different answer if you compute cohomology with coefficients in a field of characteristic P. In that case, it turns out the cohomology of this space X is non-zero in every degree. In fact, it's isomorphic to K in every degree. And the final example I want to consider is not ordinary cohomology of X, but instead the mod P K theory of X. So remember, complex K theory has to do with vector bundles. Now, if I give you any representation of the group G, you can think of it as a local system on this space X. It's a representation of the fundamental group of X or a local system on X. And in particular, it gives you a complex vector bundle on X. So that gives you a map from the representation ring of G to the complex K theory of X. And there's a theorem of Atiyah and Siegel which will tell you that if you take the representation ring mod P, that's isomorphic to the mod P K theory of X. So this is a consequence of what's called the Atiyah-Siegel completion theorem. So what the mod P K theory of X turns out to look like is the representation ring of G modulo P in every even degree and 0 in every odd degree. And this representation ring is very simple because G is just a cyclic group of order P. So G is an abelian group. That means that all of its irreducible representations are one-dimensional, and there are exactly P of them. So the representation ring of G, that's a free abelian group of rank P. And when I tensor it with Z mod P, I get a free module of rank P over Z mod P. So I want to contrast what's going on in these three situations. So note that in each case, we can view the cohomology of X as a module over the cohomology of a point. And we're in the situation where we're talking about cohomology theories that are cohomological fields, which means that all of these modules are free modules, and we can ask what are their ranks. So when K was a field of characteristic not equal to P, the cohomology of X was a module of rank 1 over the cohomology of a point. When K was a field of characteristic P, the cohomology of X with coefficients in K was a module of infinite rank over the cohomology of a point. And in the case of mod P K theory, what you got was a module of rank exactly P. And it's not hard to convince yourself that this means that these three cohomological fields are essentially different. They don't have the same characteristic in the sense of the previous slide. So in particular, that tells you this mod pk theory, it is something which is in some sense genuinely new. It's a cohomological field which is not of the same characteristic as any field that comes from algebra. So now I want to answer Ernesto's question.
What's that? First of all, what did you get there? What? Individual group or like the sum of them all?
Sorry, say that again?
Why do you get P here? Because it's all homological point, which is periodic.
Yes.
Okay. And then why does it apply that?
Well, okay, so if you have two cohomological fields,
E and E prime, let me talk not in terms of cohomology, but in terms of homology. So if you look at the E homology of X, it's a free module over the E homology of a point. That implies that the E smash E prime homology of X is a free module over the E smash E prime homology of a point, and in fact, of the same rank. And
I'm just using this particular X because I can compute exactly what these groups look like.
Mm-hmm.
all right, so now let me answer Ernesto's question from earlier about what the characteristics look like in this world of cohomological fields. So I want to describe to you the classification of cohomological fields up to this equivalence relation of having the same characteristic. So let's suppose that E has a cohomological field. And the first thing that you can do is extract from E an ordinary field. So if you look at the E cohomology of a point, every non-zero homogeneous element is invertible. So E0 of a point is going to be a field, possibly a non-commutative field in the sense of ordinary algebra. So the first question that you should ask yourself is, does this field have characteristic 0? And if the answer is yes, then it turns out you're done. Then E has the same characteristic as ordinary cohomology with coefficients in Q. So if you're interested in cohomology theories that in some sense feel like they're in characteristic 0, they're not very interesting. They're all just variants on rational cohomology. The other possibility is that this field K has characteristic P for some prime number P. And in that case, I want to do what I did on the previous slide. I want to take X to be the classifying space of the cyclic group Z mod P, and I want to compute the E cohomology of X. So the E cohomology of X is a module over the E cohomology of a point. Since E is a field, it's going to be a free module over the E cohomology of a point. And you can ask, what is its rank? So if this module has infinite rank over the E cohomology of a point, then it also turns out that you're done. In that case, E has the same characteristic as ordinary cohomology with coefficients mod P. Now the interesting case is when this module turns out to have finite rank over the E cohomology of a point. And you can prove that in this case, the rank is always a power of P. So we saw this on the previous slide for mod pk theory. What you got was a module of rank exactly P. In general, the rank will be a power of P. And in this case, we'll say that the cohomology theory E has height n. And now it turns out that height is essentially all you need to know. Yeah?
Well, I think
It
turns out that in this case, it will always be a sort of free module where
things are in even degrees. You could ask that question of, in this example, right, what we saw in the case of ordinary cohomology was you saw a copy of K in every degree. So if you want to call that infinite rank, maybe you're not taking an alternating sum, I don't know. But I mean, if we go back to this slide, this is characteristic of what you see. So when I say it's free of finite rank, you actually get a sum of p to the n copies of what you get for a cohomology of a point, and so forth. Okay, so let me state for you the classification of these cohomological fields. So for every prime number p, and every positive integer n, first, there exists a cohomological field such that the cohomology of a point is a field of characteristic P, and the cohomology theory has height n in the sense of the previous slide, so that the E cohomology of the classifying space of Z mod P is a module of rank P to the n over the E cohomology of a point. And furthermore, this cohomological field E is unique up to the equivalence relation of having the same characteristic. So, yeah.
Yeah, so let me restate it for you. So what are all the cohomological fields up to this equivalence relation of having the same characteristic? Well, they're the ones that come from algebra.
So there's the rational numbers, and for every prime number P, there's Z mod P. Then there are the ones that don't come from algebra. So each of those has a corresponding prime number P, which is the characteristic of the cohomology of a point, and also has this other integer n, which tells you how big the cohomology of BZ mod P is. And if you know that prime number P and you know n, you know all you need to know. So this cohomological field, that's referred to in this theorem, is called the nth Morava K theory. It's typically denoted by K of n, although really it depends not just on n, but also on a prime number P that's typically omitted from the notation. So this theorem, it really has two parts. There's an existence statement, which to prove that, you want to construct some cohomology theories, and then it has a uniqueness statement, which tells you that you in some sense made them all. So the existence statement is due to Jack Morava, using earlier ideas of many other mathematicians, but these cohomology theories are named after him. The uniqueness statement is much harder. This is a consequence of the nilpotence theorem of Devenatz-Hopkins-Smith. So this is it's completely non-obvious that this should be the calculation. It relies on one of the deepest theorems in stable homotopy theory. But let me give you an example. We've already met one of these Morava K theories. If you take complex K theory mod P, we observe that that's a cohomological field. We observed that the K mod P cohomology of BZ mod P was a module of rank P over the K mod P cohomology of a point. So this is the first Morava K theory. And that is the motivation for the terminology. These other Morava K theories are supposed to somehow be higher versions of ordinary K theory, or more precisely, higher versions of ordinary K theory reduced modulo P. Yeah, so you and if you wanted to study several Morava K theories and relate them, you would assume that P was fixed and N was varying.
What's that? Yeah, so I'll get to that in a moment.
So they are parameterized by P, command.
What's that?
So the parameterization is a pair of integers.
A pair of integers P comma N, where P is prime. Okay, so let me make a few remarks about that, including addressing your question.
So first, what I defined K of n to be is really just an equivalence class of cohomological fields, up to this equivalence relation of having the same characteristic. But in the literature, K of n often refers to something more specific. It refers to a particular representative of this equivalence class, which is in some sense as small as possible. So analogous to the way that in ordinary algebra, you can look at prime fields. Like the smallest field of characteristic P is Z mod P. The smallest field of characteristic 0 is the field of rational numbers. So in this world, there are also, in some sense, smallest representatives for these equivalence classes. And sometimes people use this notation to mean the smallest representative, and sometimes they don't. Second point is a warning. So when I said I was talking about fields, I mentioned I really want to talk about fields that are not necessarily commutative, and in this setting, that's really important, because unlike in classical algebra, these Morava K theories, these new fields, can never be made commutative. They're associative ring spectra, but they don't admit the structure of commutative ring spectra. What's that? No, well, complex K theory before you take it mod P is a commutative ring spectrum, but the process of taking it mod P in the world of commutative ring spectra. So, well, it doesn't admit a commutative ring structure, and it admits an associative ring structure in many different ways. That's many different ways, and that's the next point I want to make. So these K of n's, well, they're cohomological fields. So by definition, they're associative ring spectra. But typically, the ring structures on these K of n's are not unique, even when you choose the K of n's to be as small as possible. So that's a phenomenon which is sort of very different from what you would expect in classical algebra. Like, you would expect, well, if you took the complex numbers and just remembered its abelian group structure, there's probably many multiplications that you could put on it that would give you non-isomorphic fields. But if you took the rational numbers as an abelian group, well, there's only one way to give that a ring structure up to isomorphism.
Yes, the cohomology, you can choose ring structures which give you different structures on cohomology rings, topological space.
And is it also true if you say the sphere spectrum, this cone of P is also not very canonical way?
Yeah, if you take the sphere spectrum, the cone on P, and I don't know if the cone on P is even a ring in any way in that case.
That was very difficult.
What's that?
That's what creates difficulties. Otherwise,
Yeah. Yeah, if you smash with it, you can smash anything with a ring, make it a ring again. Okay.
So these ring structures is not unique, and in some sense, that's going to be the theme of the next lecture. So these Morava K theories, you can think of them as division rings in the world of homotopy. They're non-commutative fields. And in the last lecture, I talked about Brauer group in the world of algebra. If you look at division rings which have a fixed center, there's a lot of structure to that. There's sort of that gives you the Brauer group of the field which is the center. And what I would like to talk about in the next lecture is sort of similar structures that you can see in this world of homotopy theory. Slightly inaccurately, I would like to think about all of the different associative ring structures that a Morava K theory has and organize that collection of ring structures into some kind of Brauer group. So that's not exactly what's going to happen in the next lecture, but it's pretty close. So I'm going to study ring structures on Morava K theory which are as non-commutative as possible, and we're going to see that there's a lot of unexpected structure if you want to understand what all these ring structures are. Okay, that's all I have for you today. Thank you.
Any questions?
So
Yeah.
the fact that that is just get the area calculate is a decent what's the say?
Yeah, so that's when I said you need the nilpotent theorem of Devenant-Hopkins-Smith to prove this theorem. You also need it to prove this statement, as far as I know.
There's about from the time.
What's that?
And this is also a statement which is not like recent. It's like from the 90s.
Yeah.
Same package.
Right, but it's completely not obvious. The first this statement is very easy, and this statement is very hard.
And if you have something which is same as ring, then basically it must be
Speaking about your example with rank P, could you explain it again?
Sorry?
I mean, it was an example with K over P, and you said that some of the model is of rank P.
Right.
Which of them and why?
No, over the point, over the key of the point.
Okay, why?
Yeah. Oh, because so G is a cyclic group of order P. What are its representations? It has exactly P characters. So the representation ring of P is a free abelian group of rank P. And when you look at the mod PK theory of X, it's essentially the representation ring of G, tensor C mod P.
Any other questions?
Yeah. When you think of the multiplicative structures of Morava K theory, I would say that there's a numerical one, or maybe one which is actually commutative, or not
whether you're talking about like multiplication only up to homotopy, or whether you want the full A infinity structure. So if you're just talking about making Morava K-theory into a homotopy associative ring spectrum, then, well, if you demand not just that it's an algebra in the world of spectra, but that it's an algebra over Morava E-theory, then there's a unique way to make it homotopy associative and homotopy commutative when P is odd, and there's no way to make it homotopy commutative when P is 2. So in that case, there is sort of a best multiplication that you could choose, but not in the refined sense that I'm talking about, only in the homotopy associative sense. And let me remark, I said I'm going to study ring structures on Kn which are in some sense as non-commutative as possible, and that means the one you're thinking of is not allowed.
I have another one.
Yeah.
Those co-components are periodic. You can ensemble those in some way. I'm thinking of Rao-Peterson or Johnson-Wilson's thing, which are or the connected covers, for that matter, of things. Are those? What is the phenomenon on commutativity for those?
What is the well? I mean, a big unsolved question is whether or not Brown-Peterson cohomology is representable by a commutative ring spectrum. So that's open as far as I know, but I'm not. I mean, these Morava K theories can never be represented by commutative E-infinity ring spectra, and that's true for the connective covers of the Morava K theories as well. Any E-infinity ring spectrum such that P equals 0 in the cohomology of a point is automatically a module over the Eilenberg-MacLane spectrum. So it would be characteristic P in the sense that I defined earlier. It would not be like one of these new exotic things.
So yeah, one after the previous question, you said that something is an algebra over Morava E-theory.
Yeah, so I'm
What sense
getting.
exactly?
That's going to be the beginning of tomorrow's lecture. I will explain what that means.
So, I mean, it's a very nice way of introducing hate in Morava K theories. So could you give an idea more didactically to relate it to the hate of formal group law?
Yeah, so, so these Morava K theories, well, I guess not necessarily from the definition I gave, but if you have a Morava K theory where if you have a cohomological field where the cohomology of a point is concentrated in even degrees, then it will be complex oriented. So you can extract from it a formal group, and this height in the sense that I just defined here is the same as the height of that formal group. And the reason is that when you do this calculation, what is the E cohomology of X when X is BZ mod P, that is the ring of functions on the P torsion in that formal group. And the height is by definition the size of the P torsion.
You can clarify the fact that P is equal to 0, just brief a sentence. You can hold your point or something.
Sorry, say that again?
You said something that is P is equal to 0 in the cohomology of the point, then
If P is equal to 0 in the cohomology of the point, so there's a theorem due to Mohold when P equals 2 and Hopkins when P is odd, which is if you take the Eilenberg-MacLane spectrum HFP, that it has a universal property. It's the universal E2 ring spectrum in which P equals 0. So if you have anything which, it doesn't even need an E-infinity structure, it just needs an E2 structure. If you can see that P equals 0 in the homotopy, it means you have a map of E2 ring spectra from the Eilenberg-MacLane spectrum in. And that's forbidden for these Morava K theories because they're genuinely different characteristics.
so there, of course, P is equal to 0. The point is that they are not
What's that?
for them, P of course is equal to 0.
For them, P is equal to 0, so they can't admit E-infinity structures, they can't even admit E2 structures. Associative is as good as they get.
Any more questions? Well, I think Jacqueline. and the